All right. Good afternoon, and hello everyone. This is, of course, the last of our round one reviews for this year, and yeah, the SMOs basically concluded yesterday for some of you. Of course, if you are going to qualify for the second round, then it's not concluded yet, and that's going to be ideal. But I can see that it's pretty normal that the SMO Open, there is a slightly smaller group. That's because the SMO Open is generally hard, right? And if you have been doing the SMO Junior and Senior and Open, well, kudos to you. So things are going to proceed as per normal, basically. There's not much different from the usual sessions. We'll go through all the questions, but I just want to say something which is relevant to, of course, everyone, but especially those of you who are here. So this is the SMO Open we are talking about, right? So it is naturally supposed to be sort of for JC students, except that because the Open Round 2 is also the national team selection test, so therefore it is open to everyone. But nonetheless, that probably implies that if you took the SMO Open, and especially if you're watching this, you are either of a JC student's age, you're 5 years 6 or equivalent, or you are a younger student but you have some Olympiad experience, right? I don't imagine that too many of you would be taking the SMO Open at, let's say, year 1 or year 2 without having had some Olympiad experience. And so by this point in time, I think it's safe for me to say that for the SMO, especially the round 1, but for the SMO, it varies so much from year to year. And for the SMO Open, many of you will take it quite a few times. So scores will fluctuate. It's not a monotone increasing function, as much as that would be nice. So it's okay if, let's say, your scores to you don't seem to reflect your ability for general math problem solving, right? If you think that I got a lot worse than I expected, got a lot better than I expected, don't let the SMO scores define you. By this point, you've done enough Olympiads that you know there is fluctuation. And also, by now, many of you would be moving into more meaty kinds of math. Meaty kinds of math could be in terms of, let's say, round 2. It could be if, let's say, you are doing A-level further math or H3 math, or just if you are considering doing math as a course of study in university. And the round 1 of the SMO is essentially already a speed contest compared to all the math you'll be doing in future. Okay, so as much as we'll be talking about a lot of these questions here, don't get too hung up on your scores. And if you're here, answers have been circulating around. It means that you're still interested in hearing the solution. So good on you, and I appreciate you being here at this time. Now, plan is of course the same, but the questions in the SMO Open sometimes will also use some concepts which are usually only introduced in JC or A-level equivalent. So if it's A-level equivalent, many of you may be very Olympiad savvy, but may not have seen those before. So I'm going to try to just give some alternatives where possible, but not everything can be made up. For example, if you don't know what's a cross product, you can't solve the vector question, right? If you don't know what's a stationary point, you can't solve the first question. So some things can be made up, some things can't be made up. It really depends on at least whether you know the definition and how much do you know. But I'll try to give some alternatives here and there as we go along. Now, you're also going to see that in the comments as well as among your friends, there are going to be very strong opinions about this SMO Open this year. Right? Either the SMO Open this year is so easy, or the SMO Open is so hard, or it is so bad, or just very strong opinions, right? The issue is that there is a little bit of role reversal with the SMO senior. I mentioned this yesterday, which is that the easy questions this year are easy in the sense that they are just very simple applications of A-level topics, which is not ideal if you are not familiar with those A-level topics or if you haven't reached there yet in your syllabus. And so that does mean that you don't get the same freebies in, let's say, the first 5 questions as you normally do, and that may have thrown quite a number of you off. Now, conversely, it also means that if, let's say, that you do know the JC content, then there are a lot of questions which are almost like muscle memory to you, and you find to be very easy. Yes, we will get to the monkey question at some point. Okay, so without too much further ado, let's get right into the problems. And as usual, if you have any of your friends who you know wanted to join in, but maybe forgot that the session is today, then just give them a ping and ask them to pop in. If let's say that they are only interested in the first half or only the second half, then just join in at the appropriate time is also okay. Alright, so let's get straight into one of the weirder question ones that we have had in the SMO Open in recent years. You have a graph with an oblique asymptote and one of the stationary points at x equals to -4. So this is a classic A-level kind of problem. I can easily visualize this as being in one of the prelim papers. If you have any JC tools down here, you may see this pretty soon. You may already have seen this pretty soon. For those of you who don't know exactly what these mean, mathematically speaking, asymptote just means a straight line that the graph approaches. Now, if it's a vertical asymptote, that's also a place where it's undefined, but that also is still where the graph is approaching. So horizontal asymptote, that's the limit, but that's also where the graph is approaching. Now, you know that for this quadratic over linear rational function, if you were to do long division, you should expect to get a degree 1 quotient and a constant remainder, which is divided by x plus 2. So I would expect this to be something linear plus some constant over x plus 2. Now, the point is that if the graph is supposed to approach 4x minus 6, then it simply means that 4x minus 6 is going to be the quotient. That's the limiting behavior. Now I'm going to call this constant just k. I mean, I could solve for it in terms of c, but that's not very important. So y is 4x minus 6 plus some k over x plus 2. Now, of course, stationary point is the other thing. Stationary point is supposed to be where the derivative is 0. So if you differentiate this, this is supposed to be 0 at x equals to minus 4. And so this is actually going to be y, 4x minus 6 plus 16 over x plus 2. So combine it back into a single fraction and you would get A is 4, B is 2, C is 4, and your answer is 10. So the calculus portion is a little bit difficult to independently derive, right? That's admittedly true. So if let's say that you feel a little bit cheated by the first question, I can understand that. But the next few are still okay. Now, this is a question that has appeared all the way since primary school Olympiads. It also appeared in the SMO Open itself as recently as I think about the 2017 or 2018 paper. So it should be very familiar. Right, so the standard way that this goes is just the bottom sum from 1 to n. If you just write this sums from 1 to n is n plus 1 over 2, and so that is what your denominators are going to be. And so this becomes your very, very, very favorite partial fractions. And for those of you who are not so experienced with Olympiads, this is technically a JC topic, right? So partial fractions being used as method of difference is actually a JC topic. It's just that it pops up in primary school Olympiads. And there are many things that actually are introduced in primary school that are really not really covered in syllabus until A levels. There are way more than you think. So for those of you who are not A-level students yet, and then you're wondering, why does the SMO Open have so many of these super easy questions? They are easy in the sense that Olympiads introduce them very early, but they are also in the A-level syllabus, right? Let's say P&C is in A-level syllabus, these kinds of summations are in A-level syllabus, arithmetic geometric progressions are in A-level syllabus, and then some things like some basic number theory will be in H3 Math, AMGM, Cauchy-Schwarz in H3 Math. Right, so that's the reason why you seem to have these sorts of like, isn't that a bit too easy for the SMO Open kind of questions? Okay, so anyway, this is also the first of many floor functions in this paper that are redundant. It seems to be a trend from last year where they keep on giving floor functions over things that are already integers. I don't know why they're doing that, but it's probably to buffer against having even more mistakes in the papers. Okay, so answer is 2000. Now, one of the things that I also have to say I don't really like about this SMO Open paper is that it has a little bit of high correlation between problems. So there are a lot of twin problems here and there. By twin problems, I mean two different problems which are solved, or at least I would solve in practically the same way. Now that means that you kind of gain or lose two questions at a go, which leads to very high variance, right? So if let's say that you don't know three of the ideas which appeared in two questions, you lost 6 marks, which is a little bit unfortunate. So personally, that's one of the things that I did not like as much about this paper. Now, question 3 and question 4 are two different parts of the geometric series formula. The first part asking you about when the sum exists, and the second, in question 4, basically asking you to try to generalize the geometric series formula a bit. So for question 3, this is actually the world's most obvious common ratio, which, if I call this thing R, that this is just 1 plus R squared plus R cubed and so on. And this would be valued at 1 over 1 minus r. But the more important part of this, for this question, is the convergence condition. Now, the convergence condition for geometric series is that the absolute value of the common ratio should be less than 1. Which should actually make sense, because if your terms are getting bigger and bigger, the infinite series would not possibly tend towards any particular value. That would even be if r is negative, because even though it's alternating between plus and minus, if you have something like 1 minus 2 plus 4 minus 8 plus 16 minus 32 and so on, that also does not converge to anything. So the condition that you need is that the absolute value of r, this thing, is less than 1. So it becomes actually a tiny little inequality question. Okay, so I'll just solve the inequality. This is ranging from minus 1 to 1 after you open up the absolute value, multiply by 6. Now, it's possible to solve both halves of the inequality and then combine the solutions. For me personally, whenever I have got these kinds of like two-sided quadratics, I prefer to complete the square so that I can settle it all at once without having to do an slightly dubious intersection of unions of ranges. That feels a bit risky. So I'll complete the square. And if you add the 25 over 4 to both sides, and then you square root this, then this goes from half to 7 over 2. So I prefer this because then that will give you the two ranges pretty immediately, right? Either x minus 5 over 2 is between half and 7 over 2, or it's between minus 7 over 2 and minus half. Okay, so minus 1 to 2 and 3 to 6, and your answer is 7. Now for question 4, I know I have a few of my students who are in this group right now. Now for practice, I actually set a question that's similar to this, and I basically said that you just treat it like a normal geometric series question, but actually there is this clever idea of using the Maclaurin series. I didn't expect the question would actually show up with this hint. And maybe the hint actually is more confusing for some of you, because you said, what is the series expansion of 1 minus x to the negative 2? I feel like it's actually easier without the hint, to be honest. So whatever it is, let's start by opening up this sigma, because no one has ever solved a question with just looking at the sigma and said, I know exactly what's going on. It's pretty difficult to do that. So open it up just to see how it looks like. So at k equals to 0, this is 1, I'll write it as 1 over 1. The next one is 3 times half squared, so 3 over 4, then 5 over half to the power of 4, so 16, and then basically this is going to be how your series looks like. Now, I rather conspicuously did not explain the geometric series formula just now, apart from it being unnecessary for the question. It's because we can explain it down here as well, which is that if you see this, how we can try to simplify it is to multiply it by 4. And multiplying it by 4 will essentially shift everything to the left, except for 1 over 1 becomes just an extra 4. Now, subtract 4y minus y, and you get 3y equals to 4 plus 2 over 1 plus 2 over 4 plus 2 over 16. I'm sure that you can see that what we have gotten here is another. I don't really need to put 2 over 1 inside, but I'll just leave it in there. We've got ourselves an actual geometric series this time. Now, in case you weren't already aware, the geometric series derivation is precisely the same as this. So this times 4 and then subtract should not be unmotivatable if you actually knew where the formula for the standard geometric series sum comes from. Right, so if I just, for completeness sake, write it down here. And you subtract, then this is 3z equals to 4. Z is 4 over 3. So y is equal to 20 over 9. And floor of y is 2. Which is small enough that this should also cause you to just look back at the sum itself. And if you look at the sum itself, it's not that difficult to even just guess that it doesn't reach 3. Because the terms are shrinking so fast that even if you were to just make a guess of the value, you might guess that, okay, somewhere less than 2.5 is very likely to be what you would speculate to be true. Right, so this is also a question where, because it's asking for floor of y, it is very, very guessable. Now again, what is the hint actually saying? The hint is essentially that if you take 1 minus x to the negative 1, we've just written this down in the previous question. The expansion of 1 minus x to the negative 2 would come from differentiating this. And so that means that if you substitute in x is 1/4, you get something pretty close to this. you get 16 over 9 equals to 1 plus 2 over 4 plus 3 over 16 plus 4 over 64 and so on. And of course, if you substitute that back into the first one, you would have gotten 4 over 3 is 1 plus 1 over 4 plus 1 over 16, 1 over 64. And if you combine these two appropriately, you get that sum itself. So this was actually what the hint was supposed to be saying. I don't think it's very needful though. I feel like just doing the usual geometric series method is a little bit more intuitive, guessing aside of course. Okay. Question 5. Question 5, the intended method is so unrelated to the inequality sign that the inequality sign was sort of wrongly inserted. Now I know that we rage a little bit against the errors in the questions, which in both the senior and open happened this year, but both of them did in a sense also give a hint, because in the senior question they gave a general case by accident, which should tell you that it doesn't really depend so much on the numbers. And for this one, they accidentally gave you a flipped inequality sign, which tells you that don't worry too much about the inequality sign. Just look at it as, if the range of solutions is -1 to 2, then equality must hold at the boundaries -1 and 2. So equality should hold at the boundary values, so just substitute it in and compare. So this, of course, if you are wanting to be sure, you can just go back and check whether this is indeed true. But in order to have an inequality range with two boundaries excluded, and these are both continuous functions, the equality must hold at the boundary values. So numerical answer here is 3. Question 6. So this equation here has 3 equal roots. Find the value of 3q squared over r squared flawed. Now, there are a couple of equivalent ways to do this. But essentially, if you have got 3 equal roots, it means that you basically only have 2 distinct roots, right? Because this is a quartic, so you expect that you have 4 roots, and now they say there's 3 equal roots. So your roots are something like A, and B. Now, in order to do this, you have got to look for some relationship between A and B, and the main relationship is actually in the 0x cubed term, i.e. there is no x cubed term in here. The fact that there is no x cubed term in there would just tell you that by Vieta's, or comparing coefficients, the sum of roots is 0. Right? If you had written it as x minus a, x minus a, x minus a, x minus b, and compared the coefficient, you get the same conclusion, since Vieta's does come from comparing coefficients anyway. So now we have got the roots being a, and minus 3a. Personally, I prefer to just write it straight away as x minus a cubed and x plus 3a and expand and compare all the coefficients together. I feel like that's actually faster than using Vietas in this case, because it's very easy to get confused with the a times minus 3a, a times minus 3a times a, and all of that. So I prefer to just write it like this and compare coefficients to get a, q, and r. Okay, so just expand out the cube. And just compare the coefficients of the x squared, x, and the constant. For x squared, you get minus 9a squared plus 3a squared. So minus 6a squared is minus 4. And so a squared is 2/3. We'll just leave it as that. The x coefficient, you've got q on the right hand side, and the left side would be 9a cubed minus a cubed. And the constant is minus 3a to the 4. So positive r would be positive 3a to the 4. Okay, so we just compute. Q over r is 8 over 3a. And so 3q squared over r squared is equals to 64 over 3a squared, and put this back in to get 32. I'm showing hybrid methods a lot of the time because you can actually go fully Vieta or fully comparing coefficient. So whenever I show two different methods in the same question, more often than not, it's just so that I get to point out that you could use a mixture or fully one of each. Okay, question 7. The parabolas intersect at 4 distinct points which lie on a circle. Centered at AB, find modulus A minus B. At first, of course, the natural thing to ask is, can I find those points of intersection? And then after that, you realize that, well, even if you could find those points of intersection, then after that, you would need to go and look for what is their circumcenter, and that sounds really annoying. So it works if, let's say, you can find all the points, and then after that, you find the intersection of perpendicular bisectors, but I would prefer not to do that if we can do something else. Now, it is also somewhat generic here. You have got y equals to x squared minus 16x plus 50. It's just a nothing kind of parabola. It's just a parabola. So when I look at this here, I don't really see any particular significance of it. And in fact, this is generally true, that the intersection of parabolas with perpendicular exists. So for example, x equals to y squared is like pointing to the right, and then y equals to x squared minus 16x plus 50 is pointing up. So with perpendicular exists, the intersection of parabolas with perpendicular exists are always concyclic. And if you want an explanation, the explanation for this question kind of also extends to the general case. When we say intersections, of course, I mean that if there's only 3 intersections, then trivially they are concyclic. If there are fewer than 3, then this is just a redundant statement. And the way that you show this is kind of set. It is just to add the two equations together. Now you know that all your points satisfy these two equations, means they satisfy any combination of them. So I just try to combine them to get a circle's equation, and this is the equation of a circle. And so this is x minus 17 over 2 squared, y minus half squared is going to be equal to something, which doesn't really matter because it just means that the center is 17 over 2 half. And for any other parabolas, even if they are not parallel and perpendicular to the x and y axis, you can always, without loss of generality, rotate them back and then use this argument. So it's always true that the intersection of parabolas, if there are 4 intersections, the 4 intersections will be concyclic. As usual, we'll go up to question 10. Now, question 8, this is a vector question. It is, however, not a very difficult vector question, except that maybe for those of you who are using, let's say, A-level references for learning vectors, this is not usually the vector equation of the line as a cross product. The vector equation of a line is normally written as r equals to some vector u plus lambda v. It's usually written in that form, right? Meaning that this is sort of a starting position, and then v is your direction vector. So normally when it is a vector equation, you're more used to this form. But it actually just takes one transformation in order to turn this into the cross product, which is just to cross it with the direction vector v. And that's because a cross product with itself is 0. So this is equivalent to r cross v equals to u cross v. In other words, this is going to be your direction vector. This minus 1 AB, and then minus 2 C and D can just be computed by using any point on the line as a reference. Okay, so this is a slightly different looking equation of a line, but functionally it doesn't really have that big a difference in the earlier steps. So the way that you do this is actually going to be quite simple. You will take the two equations here, and then you will just solve all of them in terms of some dummy variable. Let's say if I choose my dummy variable to be x equals to lambda, then my two equations become y plus 3z equals to 4 minus lambda, and negative z equals to 6 minus 2 lambda. And so you solve for y and z in terms of lambda. Okay, so z is 2 lambda minus 6. And then you substitute in, y would be equal to negative 7 lambda plus 22. And so that means that you have found x, y, z to be lambda minus 7 lambda plus 22, 2 lambda minus 6, which if we want to write it into this form, the constants come out, and then the lambda comes out. And then you see, here it wants minus 1. Well, that's okay. Minus 1, lambda is a scalar, so you can always just flip the direction, and it is also, so we use 0, 22 minus 6 plus lambda minus 1, 7 minus 2 when we are doing our cross product. Okay, so they are the same equation because lambda is just over all reals when you do the vector equation over a straight line. Now straight away that gives you A is 7, B is minus 2. And if you want to find what is on the right hand side, you just use your 1 point, let's say 0, 22 minus 6. I just use that as my reference. Do I have something wrong? I don't think so. Yeah, so this should be fine, right? Nothing wrong here. So if you just take the cross product, the cross product is going to be, for the first component, cover up the top row and then take the 2 by 2 determinant. 22 times negative 2 minus 7 times negative 6 gives you negative 2. That's just a sanity check. The middle one, 0 times negative 2 minus negative 1 times negative 6, and then you switch the sign. The last one, you cover up, 0 minus negative 22 is 22. So this is your C and D. So your answer, when you add up all of these, is 33. For question 9, I actually covered this in my video on the SMO Open, the crash course video just a few days ago, and this is a very classic application of Cauchy-Schwarz. Very classic Cauchy-Schwarz application, which is that you can treat this thing as being dot product of 3, 4, 5 and XYZ if it helps you to see that. And so that means that it should be less than or equal to the magnitude of the two vectors multiplied together of course 3x plus 4y plus 5z straight to here, this is just Cauchy-Schwarz, right? But Cauchy-Schwarz is basically shown among other ways using a vector dot product. So take your pick whether you prefer to use vectors to help you or you prefer to just not use vectors at all. And then just square it and solve. So calculate this out and you should get 200. And the equality would happen when x to y to z is in that ratio of 3 to 4 to 5. which, if you are curious, that happens when they are just 6, 8, and 10. Yeah, and then finally, we have a very unfortunate question 10, which is just very obvious if you give it a little bit of thought, because the region of 0 less than or equals to x less than 2 in this region here, from 0 to 1, floor x is 0. From 1 to 2, floor x is 1. And so that means that you just need floor y to be 1. And so you just get a square here and a square here. So the area is 2 for 2 squares. Yeah. For those of you who are my students and you were here at the start of the year, some of you may remember a funny checkerboard graph which we actually showed. Right? And the checkerboard graph is basically just in a similar vein to this, although this is a very miniature checkerboard. It's like a 2 by 2 checkerboard. So it's actually useful to sometimes play around with graphs, just play with decimals, just experiment a bit, just try to make funny faces in decimals, and just get comfortable with how different graphs look, so that when you see something like this, you straight away know, oh, this is just some silly trivial graph. Alright, so on that note, let's take our first break for 5 minutes, and then when we're back, we will carry on with the middle section of this open round 1 paper. Okay, so question 11 is sort of the next of the paired questions that I have mentioned in this paper, right? There are a lot of questions which seem to come in pairs. So this is one of them, and it is basically very closely linked to question 19. You can see the resemblance, right? Some angle things with some trigo things and some special values things. First of all, this is a very silly condition because we know that this just tells you that a plus c is 2b and the angle sum is 180. So this just basically tells you that 3b is 180 and your angle b is 60 degrees. And angle b is 60 degrees. So your equation, the minus root 2 over cosine b, the cosine b is just half. Right? And you have, of course, a plus c is 120 degrees. So now if you have got this 1 over cosine A and 1 over cosine C summing to negative 2 root 2, one way is to substitute C equals to 120 minus A. That can work. I'm going to do something here because that will also sort of explain what I mean by the association with question 19. Right, which is that I prefer to leave it actually as just A and C. Okay, and just multiply it over first. And then to just use the product to sum on the right and sum to product on the left. A plus C is 120, tells me that whatever I produce, one of them is going to be nice. Okay, so for senior, I will normally explain the sum to product a little bit more carefully. At this point, I will just sort of get straight into what it is. Now, the reason why I want to do it also because I know A minus C over 2 is going to show up and A plus C over 2 is exactly the angle that I want. And then for the other one, 2 cosine A cosine C is cosine A plus C plus cosine A minus C, which is just double of what I want. So now I'm just going to fill in all the details and I'm going to just let x be that cosine that I want. So first of all, cosine 60 degrees is half, so that cancels with 2 and I'm just left with x on the left. Now on the right, cosine 120 degrees is minus half, and cosine A minus C using my double angle formula is 2 cosine squared A minus C over 2 minus 1. So this is just a quadratic. If you shift everything over to the left, this is the quadratic which we are going to be left with. And so by whatever means you want, whether by just guessing or by putting it into your quadratic formula or by actually attempting to factorize it, which is not as bad as you think, you get x is equal to negative 3 over 2 root 2 or 1 over root 2, which obviously the first one is not going to be possible because it's a cosine, and this would be less than negative 1. So x is 1 over root 2. In other words, actually cosine a minus c over 2 is cosine 45 degrees. So your answer would be 1011. Yeah, from time to time, I do mention places where you can exploit the integer condition. I don't want to mention that in every single question, just because that's going to overtake the entire discussion. I still want to explain the solutions as they stand. How would you solve the question in full detail? But if you see various places where you think you can get the answer out because it's an integer, because it's positive, or just by accurate drawing or whatever, feel free to share. Right? I mean, in practical SMO conditions, you just want to do whatever gives you the marks that you can get. Now, question 12. This is a little bit of a troll question, but if you actually search this out, this is adapted from the Bay Area Math Olympiad from a few years ago. I can't remember which year, around 2019? Somewhere around there, right? Just search it out if you want to see where it originally came from. Now, the concept here is actually just very simple. Right? If you remember, in fact, from one of the things I mentioned from my crash course video, we talked about monotone functions. We talked about how we can talk about function properties. This is the most monotone of monotone function. This is a linear in x. So as long as it's linear in x, all you need to do is just to try to play a higher or lower game. And there are just coincidentally 2023 fractions in order to get 2023. So by inspection, x is 2020. Now, I know every time when I write something like this, someone asks, how do we find this systematically? That's kind of missing the point, right? The point is that by inspection is only allowed because there's only one solution for a linear equation. So that's why you don't have to find it systematically. There is no other solution, for sure. Did I use this as an SMO mock paper? I remember that I did use that Bay Area Math Olympiad question somewhere. I have no recollection where I used it. So if I used it actually in the mock paper, then good for you. I don't remember where I used it. I did use it somewhere. Okay, question 13. This is a classic pattern recognition kind of algebra question. And by pattern recognition, I mean that in two different ways. The first is that if you have done all the SMO Junior questions in years past, or maybe you even just took the SMO Junior and so you have been practicing SMO Junior papers, you know what this always does, right? Your x minus 1 over x and x plus 1 over x are just going to give you all the x squared plus 1 over x squared, x cubed plus 1 over x cubed, x to the 4 plus 1 over x to the 4, and so on. That's what always happens. So that's the first thing, right? Because we have seen x minus 1 over x in that context before, we suspect that is likely to be how these things are meant to be used. Now, the second thing is that you notice that both of them start with 10 and end with a constant, and then the two in the middle both sum to 10. 8 plus 2 and 6 plus 4. In other words, there is actually some symmetry about x to the power of 5. Which is why the first thing I'm going to do is to divide the top and bottom by x to the power of 5. in order to get it into the territory we are a lot more familiar with. Now, of course, this is plus, right? So since we have minus, we can just do the very quick transition over to x plus 1 over x. Right, x plus 1 over x squared and x minus 1 over x squared are going to differ by 4. So this would be square root 13. But I'm just going to call this thing a first for now. Don't want to spam square root 13s everywhere. I just want to write them all in terms of a, and then we can just move along pretty smoothly. So first of all, to get to the cube one, x cubed plus 1 over x cubed is going to be this a cubed minus 3a. That's your binomial theorem. Now, to get to the one with 5, you can take this x plus 1 over x to the power of 5 as well. And your coefficients are 1, 5, 10, 10, 5, 1. So you're going to have to minus off 5 times of this and 10 times of this, which we can write back in terms of a again. Great, so we have now got all of these things in terms of a prepared. So let's go back and just put it in. So when you add those two together, you get a to the 5 minus 4a cubed plus 2a. When you add the other two together, you just get a to the 5 minus 5a squared plus 6a, and then cancel off one factor of a. I don't need to simplify this anymore. I just wanted to make sure that, sorry, this is a 3. I just wanted to make sure that I only put in the square root 13 when it is convenient. So now it's convenient because a squared is 13. So you can put it in as your value. And what you should get is 119 over 110. Okay. Question 14. Circle again. How many times are they going to ask us about circles today? So this is a very obvious equation of a circle, and it's also a very nicely positioned circle. So I mean, the set of all possible pairs is literally the set of points on the circle. Radius is 3, center is 4, 3. And S is the largest possible value of y over x. Now, you can think of this in a couple of different ways, right? One is that you can say that if s is the largest possible value of y over x, that means y equals to sx intersects the graph, and you want the maximum gradient of a straight line going through the origin. You can also just substitute y equals to sx into the equation and then just discriminant bash it again. But I'm going to do the geometric one because that's a bit faster. Basically, if you want to make the maximum, you just imagine tilting it from the x-axis and pivoting upwards until you get to the tangent line. Now, y over x is going to be the gradient of this line, but the easier way to also get that, instead of finding the intersection, is to use the fact that the gradient also is going to be tangent of the angle that it forms. And the angle that it forms is easy to work with because of the fact that this circle touches your x-axis. In other words, y over x equals to tangent 2 theta, and your tangent theta opposite over adjacent is 3/4. See, yet another redundant floor function. We've had quite a lot already today. Okay, question 15. It looks a bit like a junior question, right? The junior question was vaguely also something like this with positive integers and a bound. It's kind of also a little bit even easier to list than the junior question because your x more or less can't go beyond it, like somewhere in the range of 12 or 13. I'm a bit lazy to calculate it, but x can't be too big because 16x squared alone can easily go past 2023. So even if you just wanted to list out with cases, it's not going to take actually forever. And if you just try a few of them, this question happens to have a few cases that all give you the same maximum value, which also means that it is very easy to arrive at the correct answer, even if your guessing was not comprehensive. But not too surprisingly, the intended method has to do with the fact that this is roughly almost 4x plus y squared. It is 4x plus y squared with a missing xy, so you can write it like this. Now, my strategy is that I want to bound 4x plus y. And it's kind of funny, right? Because in order to get the maximum value of xy, it means that what I'm going to do is I'm going to get a maximum value of xy. And how am I going to get the maximum value of xy? Well, to get the maximum value of xy, I am going to rely on a lousy upper bound on 4x plus y. In other words, I am going to do a self-improving bound. Now this is not really new, right? If you know, let's say, Newton's approximation for roots, Newton-Raphson, or any even methods for solving differential equations, self-improvement is one of the ways that we solve a lot of things. So this actually is quite sensible. Now my lousy upper bound is going to be something like this. I'm just going to say that 4x plus y squared is 16x squared plus y squared plus 8xy, right? The only thing that makes it not is the 7. So I say that, well, 7 over 8 of 4x plus y squared would be smaller than this. So that gives me a lousy upper bound. But it's a lousy upper bound that is a constant. And so 4x plus y squared is less than or equal to 2312. It's not something that I'm saying equality can actually hold. In fact, it's a strict inequality because this one's also strict. That 7 over 8 is strictly smaller than. But it just gives me a bound that 4x plus y is going to be less than 48. So this is a strict bound. I guess if you know the answer, you know that's actually not that lousy. But when I say lousy, I meant no need to be good upper bound. Now 4x plus y is less than 48 means that by AMGM, two times of the geometric mean is less than 48. And so xy is at most 144, 12 squared. So now I can push it back in again, and this would tell me that 4x plus y squared is less than or equal to this plus this is 2167. And so that improves it down from less than 48 to it is at most 46. (46 squared is 2116. So this satisfies the condition as long as my 2023 plus xy is at least 46 squared. So which means that I just need to select xy to be more than a difference, which is very easy, right? So that means that there is no problem with getting 46 in a bunch of actually different ways. It's attainable. Sorry. It is attainable if, let's say, xy, if you went for something like, let's say, 8 and 14, that's fine. If you went with something like 7 and 18, that's also fine. If you went for something with 6 and 22, it's also fine. So there's just quite a number of ways you can get it. Which is why this is, again, pretty easy to guess, because if you had just tried different values of x somewhere in the mid-range, they all give you the same maximum, so they all work. But the answer indeed is 46, and this is how we have justified 47 and above being impossible. Okay, question 16. Quick spoiler alert, if you're wondering where did the person or the question setter come up with this very clever looking thing, well, X the golden ratio. The golden ratio has lots of identities that you can associate with it. You didn't know that, of course, but X is actually the golden ratio, right? Root 5 plus 1 over 2. So many times questions are set with like a special constant in mind which has nice properties, and then a very ugly looking equation is thereby manufactured, but you do not need to worry about the details. Just solve it in the most boring way possible, and then we'll see what happens. Okay, so that's what I chose to do. I just did the usual, which is to try to square it. I personally prefer to separate the square roots before squaring, even though I don't really know what's the best combination of this, but I don't want to have to square root the product of those two things. It looks like it may not be nice, so don't know. but let's square this. Okay, so at least a 1 over x will cancel out in this squaring. I will rearrange everything and then we go again. So square again. This will be x to the 4, 2x cubed, x squared. There is 2x squared from the front and back and another x squared from the middle, so 3x squared minus 2x from the 2 at the back and then plus 1. And then shift it over, you get x to the 4 minus 2x cubed minus x squared. So there's a minus 4x here, becomes plus 2x plus 1. Now this probably means something, right? Because, I mean, this is supposed to be almost like find x. So if I get this quartic here, it should be something that you can actually factorize. Now there are a couple of ways that you could proceed. Now both of these are semi-speculative, of course, but it all comes down to the fact that you know that this thing here must have real roots, and in fact it must have a real root which at least has a moderately nice expression. So the ugly way to do this would be to substitute a equals to 2x minus 1 into here, expand it, and then notice that something nice happens. I don't really feel like doing that, but if we were to go the opposite way and expand the 2x minus 1 to the power of 4, we may notice something interesting. So expansion in progress. Now, what I notice, which may not really seem like very much, is that at least this and this are both in a 1:2 ratio for your coefficients. So I can lift it up here at the bottom and get something that at least matches the first two coefficients. So I multiply it by 16. Which means that if I were to just subtract this off, which is subtracting 0, I'm left with 40x squared minus 40x minus 50, right? Just subtract this off. Now once again, what I realize is that this also is related to 2x minus 1 via its square. 2x minus 1 squared is 4x squared minus 4x minus 1. So if I complete the square, then you get the rather humorous realization that, well, we didn't find the value, but we have actually found the factorization that is lurking behind this thing all along. Right, it's 2x minus 1 squared minus 5 squared is equal to 0. Now, I'm saying all of this, of course, if you just notice straight away, this is x minus 1 squared, then good for you, right? But if you are going to say, well, how am I supposed to think of specifically x squared minus x minus 1? Then maybe thinking of 2x minus 1 makes more sense because that's in the question. But if you say, no, I mean, I would guess that it's a square. Well, agreed, that's fine. So, I said speculative, right? So, actually, if you guess that there exists a factorization, and then you try to compare coefficients, both ways is fine. So this will give you that golden ratio, but here I don't need to actually find x. I can just straight away get 2x minus 1 to the 4 is 25. Okay, so let's end on question 17 because that's a little bit of like a quick and easy answer, as well as interesting explanation. Now, the quick and easy answer is just simply that if you just suspect that they can't possibly make you factorize a huge 999999999, then you just try something small and you find that actually by inspection it is 999 is 27 times 37 and the answer is 64, right? Again, this is the latest somewhat guessable question. So let me just talk about how you can actually justify that this is the only solution. Now, many of the questions in the open round 1, as I mentioned in the crash course video, are like junior round 2 questions, where of course you do not need to supply a proof. So if you want to give yourself like some like so-called entry-level round 2 practice, try proving all the questions that you guessed by some so-called unintended approaches. And sometimes it will give you a proper solution. So let's just try to do that. Now, I will call my two positive integers that differ by 10 x minus 5 and x plus 5 for symmetry. And all the digits in the representation are 9, means that it is just some 10 to the power of k minus 1. Right, so if they are supposed to be equal, difference of squares, then you get x squared is 10 to the k plus 24. So I mean, the first few cases of k, right, because k could be any positive integer. If k is 1, then of course that would be 9, but that doesn't really count. So in any other situation, why can't it be a square apart from this one special? So let's say you take 34, then after that 124, 1024 is the one that works. This is 32 squared. And then let's say we just look at some of this stuff, like what good reason is there that we can be certain none of these are squares? Well, now one of the things is that you could say that for those of them which are case even, this is just very slightly more than 10,000. So it can't hit the next square. And likewise for all of the even values of k. But the easiest explanation is just that if k is anything more than 3, then you know that 2 to the power of 4 divides 10 to the k, but 2 cubed double divides 24, meaning that the highest power of 2 in 24 is only 2 cubed, meaning that you're going to have the right hand side is divisible by 2 cubed and no more than that. So you have a odd number in your prime factorization, 2 cubed, and so therefore it cannot be a square. Alright, so let's take our second break here, and when we are back we will wrap up with the remaining problems. Yeah, just a quick shout out to any of you who have been taking the China Western selection today. If you're watching this after, or if you are joining right now, hope it went well for you. Right, so thanks for sticking around. Yeah, down to the home stretch of the paper, right? And this back half is what I can broadly describe as a little bit, I don't know, disappointing? Is that the right word? Well, it was a bit anticlimactic because those of you who were in the senior stream yesterday, I told you I hadn't looked at the open paper. I didn't really have the time. So as of then, so when I went back then, I looked at it just roughly. I thought, oh no, like this back part looks like it may take a bit of time to work out. And then when I actually read each question, like let's say the geometry diagrams, when I had actually some time to go and draw out a diagram, or some of these sequence questions where I actually had some time to actually write down, it all resolved a bit faster than I anticipated. So it sort of was a bit deflating, like, oh, that is the solution already a bit faster than I expected. So I can understand many of you therefore having been sort of tricked into trying the wrong questions, because a lot of the difficult looking questions are not very difficult. So it is a little bit unfortunate in that respect. So question 18. Continuing on with what we usually say for all sequence questions, try to write down the first few terms of the sequence. In the case of my question with ANs, BNs, and SNs, AN is the sequence, right? So SN is the series and BN is just something derived from AN. So you want to just find out what's AN. But you're not given any starting values. So what do? Well, it's all positive integers n, right? So you just start off with, I can let n equals to 1 in here, and that will give me an initial value. Okay, so let me just square this first, get rid of the square root. 2 equals to 2 root 2 Sn. So square this, an squared plus 4an plus 4 equals to 8 Sn. Now in the case of n equals to 1, S1 is A1. And this shifts over and you actually just get A1 minus 2 squared is 0. So A1 is 2. But in general, you can pretty much do the same thing, which is that I can just take AN out from the rest of it, shift it over. And so therefore AN minus 2 squared is 8 times of the sum of everything so far. So based on that, it's quite easy to just get the next few terms, right? S1 is 2, 8 times 2 is 16, square root of 16 is 4, so the next term will be 4 plus 2 is 6, and then the sum is 8. Sum is 8, 8 times 8 is of course 64, square root you get 8 again, 8 plus 2 is 10. The sum is going to be 18, and I think it is fairly obvious what is going on with this sequence. Right, so it is not very difficult to, by induction, conclude that just AN is 4n minus 2. Great, so we know AN. Now let's see what does BN give us when we add up this B1 to BN. So there's a big one, half. The first one, you have A2 over A1 plus A1 over A2. And then you have A3 over A2 plus A2 over A3. And so on until you have AN plus 1 over AN plus AN over AN plus 1. And most of these actually if you notice the adjacent ones, okay, so this one I didn't write down, but next one will be a4 over a3, and then so on. a1 plus a3 over a2, because this is an arithmetic progression, those are all just going to become 2. Now a2 over a1 is literally just fixed as 3. And then this last leftover, an over n plus 1, this one approaches 1 as n is very big. So this tends towards, you have got 3, 2, n minus 1 times, and a 1, which is just going to be n plus 1. And so your answer is 1, which can also have been guessed quite easily if you just took the first few terms of this. At least after you found what's a1, 2, 3, 4, it's pretty easy to guess this. Question 19. If you just joined in, I said about 40 minutes ago that question 11 can be handled pretty much the same way as this. And that's because this is screaming out to be used as a sum to product on the top and bottom. So again, another question that is sort of in a pair. You cancel this, and this is just tangent a plus b over 2. And a plus b is 180 minus c. And so after all of this, you just get tangent c is tangent of 90 minus c over 2. And it's pretty easy to see that that should just give you c is 60 degrees. Right? When you equate the two, angles c is 60 degrees. Well, we've heard that before, haven't we? This one's even worse because it then says that sine of b minus a is cosine c. Cosine c is half, and so sine b minus a is half, means b minus a is 30 degrees. And so since they add up to the other 120 degrees, it means that b is 75 degrees and a is 45 degrees. So you have got a 45, 60, 75 triangle. Well, that's pretty good because 2 out of the 3 angles are very nice. And the easiest way to resolve this is just to use the 45 and 60 and just drop a perpendicular down here. Right, so if this value here is x, then you get root 3x and root 3x, and then your area this resolves to just be x equals to square root 2. Okay, so therefore a is 2 root 2, c equals to 2 root 3, and so your answer is 20. Okay, so you're all waiting for question 20, right? I have nothing to say about question 20, you know. When I say I have nothing to say, is that I'm not a representative of the Singapore Math Society. I don't actually have an explanation to you. I cannot say anything other than it is going to be voided for sure, because the question, this is not an operating error, this is a mathematical error. Meaning that this thing here, this functional equation has no solution. Now, if you actually just took a look at old SMO open problem, I've checked, right? Just look back at 2006 question 3. It's the same exact functional, except that the constant is 2 at the back. That was the question. That is solvable, and the function would just have been gx is 1. Put aside the initial condition. So clearly somebody thought that it might be a good idea to add an extra constant behind to make it 2023, but then not realizing that this functional equation simply has no solution. Now, it's no solution because if we just swap the rows of x and y, then you just get repeated, repeated, and then not repeated, repeated, and so comparing, it means that these must be the same for any xy. In other words, gx minus x is a constant, so gx is x plus c for some constant c. But that is necessary but not sufficient. So those of you who have heard half the story might say, oh, so that means that you can just have gx is x plus 4. No, that doesn't work. And in fact, no constants work for this. Because if you just try substituting back in, xy plus 1 plus c should always be equal to x plus c, y plus c, minus y plus c, minus x plus 2023. Now, if you compare the coefficients of x and y, c should be 1. C can only be 1. But that doesn't even satisfy the constant, right? If you compare the constant terms, one plus c is supposed to be c squared minus c plus 2023. Well, that's not going to work out. In other words, this here and this here already contradict before we even talk about the condition in question. So this is definitely not going to work out. Yeah, coincidentally enough, right, in the video that I shot, I picked a question that had an error inside. That question has an error, but it has sort of an intended approach. It was just sort of an accident. So if they had changed it into A, B, C, D are complex numbers for that question I referenced, it would have been okay, but this one just simply does not work. So yes, it'll be voided, no questions asked. Whether everyone gets a mark or everyone doesn't get a mark is kind of beside the point here. Okay, so for the benefit of anyone who is watching this a year later, the SMO has had a non-trivial number of mishaps of this sort. So if something really looks weird, just skip the question. Don't spend too much time on any given question in case history repeats itself again. Okay, so on to the back page. Question 21. This is a very good example of try to learn how to do circle geometry without drawing any circles. Because you're going to probably take about 9 attempts before you're going to actually manage to draw the triangle such that the lines BA and CE are really tangent to the circumcircle at A and E respectively. It's not going to happen the first a lot of times that you try. So I'm going to draw a deliberately, like just a normal person kind of diagram. I know it doesn't actually work as a good diagram because I know how the things are supposed to work like at the end, but you will know when you're solving it. I wouldn't know when I was solving it. So let's just put this all down first and we shall see. So D and E are midpoints. Now BA and CE are supposed to be tangent to the circumcircle of ADE. So I definitely need to draw CE at A and E respectively. So I'm going to, well, just put in a very, very faint and like just rough kind of circle. This is not meant to be used for really anything, and we might just erase it back later if we need to. Now you can actually do this without the circle, or if you drew in the circle, then hopefully your diagram is a bit better than mine. The reason is that tangent gives you a couple of things, right? Tangent can give you your alternate segment, that's your angle relation, or it can give you your power of a point slash tangent secant, which is your length relation. So you want to make sure that you just mark out all of those information first. Okay, so I'm going to just look at the midpoint information and call these two things X and call these two things Y. And the tangent secant theorem tells me that BA squared should be BE times BD. So BA should be square root 2y. And on the other side, CD times CA should be CE squared. So that should be square root 2x. That's part of it. But the whole thing that you're supposed to get is actually similar triangles. Now your alternate segment is supposed to give you that these are equal angles. That one looks reasonable. It's also supposed to give you that this is equal to this. This does not look very reasonable. But what those all come down to, both the alternate segment theorem as well as your tangent secant, is your similar triangles. Triangle BAE is supposed to be similar to triangle BDA, as well as triangle CDE is supposed to be similar to triangle CEA. So both of them are actually going to tell you the length of AE. Now this one tells you that if you substitute in, AE is going to be x over square root 2. The other one is going to tell you that AE is y square root 2. Which means that collectively, x is equal to 2y. And if x equals to 2y, then we basically know just about every single length in this figure up to similarity. Okay, so let's just draw this thing again out on the other side without the circle. So I'll write everything now in terms of just y. So this is 2y, 2y, 2 root 2y, y, and y, root 2y, and then root 2y. So as you can see, obviously ABE is an isosceles triangle, right? No, so this is a terrible drawing. Now you're given one piece of information, which is the circumradius. Yeah, again, the slightly annoying thing is that question 22 also mentions circumradius. So you have 21 and 22 are two geometry questions that are again coupled together, and they are coupled together by your extended sine rule. Now, your extended sine rule is that A over sine A and all of that stuff are equal to 2 times of the circumradius. This is pretty easy to just show if you actually drew in a circle in a less cluttered diagram, but I'm not going to show it here. In other words, all you need to do is just a little bit of trigo in order to find out what is y, and then we will be pretty much done, because if we find out what is y, then everything including your the circumradius is all going to just not matter anymore. So use the cosine rule on triangle ADE. Cosine rule on triangle ADE should give you that cosine ADE is 3/4. And then your sine is going to be root 7 over 4. So of course I'm using triangle ADE because the circumradius given is that triangle's circumradius. Okay, and so therefore my AE is equal to 2r times this value. And then from here, I am running out of space, but we have got y, and then from y we can just calculate the area of ADE, and then the full triangle area is 4 times of ADE. Now, you would get, if you have worked it out correctly after the simplification, as a quick check, y should actually be the 4th root of 7. And your final answer should be 7. So I'll leave the details to you for this one. And if this is a little bit annoying to you, I should just say that for the SMO Open, geometry questions tend to be very much just length bashing. or just length bashing with a bit of trigo, or trigo with a little bit of similar triangles, or something like that. This tends to be a lot of the open round 1 kind of problem profile. Okay. 22. Now, the moment I read this question, it just looks incredibly like a super special case. Right? There are so many equal lengths, so it should be quite nice. Now, we are told that ABC is less than 90 degrees and sine of ABC is 4/5. So let's just draw something like this. And then we get all the extensions that I mentioned. Point K is on the extension of BC such that DC is equal to DK. So you've got 3 equal lengths here. And then you've got L is on the extension of DC such that BC equals to BL. So you have also got 3 equal lengths down there. Let me highlight the equal lengths. Those of you in my classes, you know I always like to just use color to help to keep track of things. I think it does actually do a lot of good if you want to have a bit more of a visual intuition for geometry. Now, the bisector of angle CDK and angle LBC, those are going to be also perpendicular bisectors. Intersects at Q. Now, the circumradius of ABD is 25. Find the length of KL. The first thing that comes to my mind is that why the circumradius of ABD? What does ABD have to do with anything? I mean, ABD is part of the parallelogram, but what does it have to do with everything? Now, the answer lies in the fact that all isosceles trapeziums are cyclic. And more specifically, a trapezium is cyclic if and only if it is isosceles. Now that means that because we have 2 overlapping isosceles trapeziums, ABLD is concyclic and ABKD is also concyclic. So ABD is in common, and then L and K are also part of it, which just means that all of them actually are concyclic. So 5 points lie on the same circle. Okay, that's a poor choice of color. But if you just do a touch of angle chasing, the funny thing is that Q is also on that circle, and then the question seemed to have forgotten to use Q for anything at all. Realize that? Well, what is Q doing? I'm not quite sure. It feels like something else was meant to be asked, because why would you construct this thing and not do anything with it? Now, if you do a bit of angle tracing, actually, this dkc equals to dck equals to dq. So this is also on the circle, but I have no idea what it's actually doing. So it would be 6 points on the same circle. But they did ask for KL, right? So I mean, let's just go with KL. Now KL is going to be on the circle, and so that means that you can use back the extended sign rule again. Now if you use, let's say, the triangle KBL, then KL is going to be 2 times the circumradius times sine of KBL, which surely can't be very difficult to find, considering that we are given a sign in the question and we have not used that at all. Right? And the sign in the question is of that blue angle, which I've marked a few of, so let's just continue marking all the other places where it appears. So this surely can't be very difficult to do, because KBL is just 180 minus 2 times of that angle. So 180 minus 2 times of that, sine will be the same for supplementary angles. And so you can just use your double angle. Okay, so sine is 4/5, cosine will be 3/5. And so your answer should be 48. I have no idea what's going on with a redundant point, right? Why would you give a redundant point? It's like a semi-change of mind in what to ask, but then didn't remove that. Q is a nice point, right? So I'm not sure what was actually the intended question. Oh. And we are on to the monkey question at last. The monkey question: determine the maximum number k such that there must be k monkeys picking up the same number of peanuts. Whenever you are presented with something like this, there's two possibilities. One is that immediately it makes sense to you, or you've seen something like that before. The other is that you are like, what does the maximum even mean? Why should there be a maximum? So you can sort of just ask yourself, what kind of guarantee is that? And if you don't see any guarantee, ask yourself, okay, what happens if just k is 1? Meaning that there are no monkeys which are repeating. Now k is 1, then the 200 monkeys, the total number of peanuts would at least have to be all different, and this is very big. This is a lot more than 3,000. And so we realized that the problem is that if you want to make them all take a different number, it's too big. So you need to have a lot of repetition of the smaller numbers in order to even get it to be under 3000. Right, to get it to under 3000, we can make quite a big jump in order to save some time. Let's jump all the way to 5. And you'll see that it's still going to be way too much, right? So if anything can be repeated at most 5 times, this is 3900, still too big. If you go with 6, then 200 divided by 6 is 33, remainder 2. So this will be your total. This is a little bit more than 3000, right? So we don't have to calculate it in full, right? We just need to know, okay, this still exceeds. Now, the next one, k equals to 7, you'll see does not exceed. So 200 divided by 7 is going to be 28, remainder 4. And this is quite clearly going to be less than 3000. Now we don't need to calculate this. The point is just that however much less this is, it shows that if I allow repetition of up to 7 times, it can work. If I only allow repetition of up to 6 times, it cannot work. And so this tells you that the answer is 7. Yeah, in fact, when I first did the working as well, I also did not read the very prominent notice that was given that says that it is possible that some lazy monkeys may not pick up any peanuts at all. It doesn't matter, right? It does not change the correct answer. So in this case, if you didn't notice that, not too much of a problem. Last 2 questions, and you can see that even for this SMO open paper, we seem to be keeping quite good time. It is within, significantly within 2.5 hours. The last 2 questions are non-trivial, but they're not long, not that long, right? Not as bad as like the question 23 from senior. For this problem, when I first read it, I thought that it was very difficult because I misread it, and I thought that the circles were touching each other and the ellipse. Now, if you read it carefully, only the first one is touching the ellipse, the last one should be touching the ellipse, and then the rest of the circles are just touching each other. Which means that you have an ellipse, and then that's a terrible ellipse. You have an ellipse, and then you just want to sort of draw a bunch of circles just straight across. This is something like what you want to do. Now, you want the smallest possible value of n. The smallest possible value of n basically means that you want to have the radius to be as big as possible so that you can sort of cross from left to right as quickly as possible. So the question that I then ask is, why can't I just have a super big circle? And I think intuitively it makes sense that you can't have a super big circle because if let's say that you have got a very big circle. It's going to actually intersect this ellipse again. So that's not really tangent anymore, right? If it touches somewhere but it's also intersecting in two different places, we would not call it a tangent circle. Otherwise, I mean, I could, this is also not going to be an internally tangent, even if we just grant that that is tangent. So we need to make sure that the circle stays inside. And smaller circles are always going to stay inside. Bigger circles are always going to go outside. So we just need to find what is the cutoff point between the circle managing to fit inside just perfectly and the circles just going to intersect the ellipse in multiple places. As long as I find that one circle, the rest of the circles in the middle are not the problem. Right, so I just want to figure out what is the possible size of C1. Right, so possible radius, that is. The most direct and boring way would just to be, okay, let's C1, since it has to be going through this point, the center, you just shift it R units to the right. So C1 would be x minus negative root 2023 plus R squared and y squared equals to R squared, right? And then after that, just combine with the ellipse and discriminant again. That is possible, but A, very familiar, B, very boring, and C, pretty messy. So I will also leave that to you, and instead I will just tell you a fact, which is going to be enough to resolve this immediately, which is just a property of ellipses. Now, I suspect that maybe it was intended to test whether you know the property of an ellipse in this question 24, since after all it is an open paper and conic sections are in A-level further math. So there is this notion of a radius of curvature. Now the radius of curvature of any curve basically means that instead of a tangent line, if you make a tangent circle, how big would be the radius of that circle? So for example, a straight line, the radius of curvature will be infinite. Now the radius of curvature at the endpoints of your semi-major and semi-minor axis, which is these 4 points, right? So at these 2 points basically is what I care about for now. It's going to be based on an ellipse in this general form. It will be 333 over square root 2023. And for the other one, it would be 2023 over square root 333. I hope it makes sense that it's in that order at least. If we talk about the top and bottom ones, then the radius of curvature should be bigger because it would be so-called touching a bigger circle, right? The ones at the left and right are narrower. So if the radius of curvature is this, that means that this circle is the one that is going to so-called wrap perfectly in it. And any other is going to be exceeding it and therefore intersecting the ellipse again. And so since you have got n circles of this radius, and it's supposed to be the sum of the radii will be square root 2023, it's going to be square root 2023 divided by this. That is your lower bound, which is this is a little bit more than 6. So therefore the minimum is going to be 7. You just adjust the radius to be literally the square root 2023 over 7, and then you'll be fine. So just as a reference, I just took the diagram, or I just generated a diagram where this is the radius of curvature. This is the biggest possible circle. The actual one's a little bit smaller. Of course, you don't need to do this in the SMO, but visually, this is how it should look like. It should wrap as closely as possible around that 2 endpoints. Now, finally, question 25. We are reaching the end, and this is a question where it is screaming out something difference of squares. Right? We have got the SMO junior version of difference of squares, SMO senior version of difference of squares, and so this is the SMO opens difference of squares. Before we do anything too complicated, the first thing that you have to take note of is that it says let P greater than 2023 be a prime. So P is fixed. If you thought that the question is asking you how many pairs N and P are going to satisfy this, that's a much bigger problem. Now, the second thing that you want to notice is that this here is almost a perfect square already. Now, it had better not be, otherwise the answer would be infinite. But it's almost a perfect square because if you were to rearrange this, it actually is almost a perfect square, except that there is this minus and plus. It's almost a perfect square. So going all the way back to your junior completing the square kind of questions where they say something like, okay, like n squared minus 10n plus 4 is a perfect square, and then you just complete the square, something like that. And then after that, you just make it into a difference of squares, right? This is the usual procedure for junior style difference of squares style of entire equations. For this one, I also want to kind of quasi-complete the square by making this almost into a perfect square. So since this is so like a perfect square, I would just say that this is really almost as if it's a perfect square. It's almost as if it is n minus p minus 2023 squared, but that would have been a minus instead of a plus. So the difference is in the coefficient of p. Here in what I wrote, it is actually plus 2 times 2023 times p, whereas it should have been minus. So that's going to be the leftover. So this is sort of completing the square, and it is logical because what you wanted from the so-called vanilla version of the question is that this thing can be factorized. And so therefore you know all its factors and you can list. Here, you also know its factors because p is a prime. So now if I set this to be equal to m squared and just make this into the usual difference of squares, I can still factorize this and this. And on the left side, I'm sure you know the factorization of 2023. P is just something bigger. So what's the significance of P is something bigger? Well, it's not terribly important actually. The main thing is that we just know that P is not going to interfere with 2, 7, and 17. And so when I want to split this up into two sides, the only condition that you need is for both of these to have the same parity. As long as they have the same parity, then if you want to find n, you just take the sum of the two factors, divide by 2, and then add p and add 2023, right? So it doesn't matter what p is, as long as they're the same parity, then n exists. So if they have to contain the same parity, that means that, first of all, I need to put 2 on each side. Second of all, well, one more significance of P being greater than 2023 is just that P should go onto the bigger one. Right, so the plus M should be the bigger one, and the minus M1 will be the smaller one, so the P doesn't go there. And then what's left over in here is just your 2023, the 7 times 17 squared, can be split up in any way you like. And since 7 times 17 squared, 2023, has 6 factors, so you get just 6 combinations, and each of them gives you one value of n. And there you have it. This is our SMO open paper for 2023. For those of you who joined in late, again, the general comment that I can make is that this paper was very polarizing because after talking through all these solutions, I can't really say that there are that many impossibly hard questions. There are also quite a lot of questions that are guessable. But at the same time, it's not objectively that easy, as many of you have attested to. So, in response to all of the questions about cutoffs, I don't know, but just off the top of my head, I don't envision it changing that much from the range of score. So last year, the cutoff was somewhere in the 13-ish range, and if you're talking about now the one voided question, so let's say you take away one from that, that would be 12. Could be a bit higher, a bit lower, depending on whether they want more or less qualifiers for round 2. Somewhere in that vicinity is probably going to be what you would expect. Okay, so yeah, if there are any other questions, I'll just stick around for a few moments. If not, then we will just wrap up this session here. And all the best for round 2 if you're taking it. I guess that is all I have to say for now. So I'll go off camera first, and if you have any other questions, just do feel free to drop them in the chat. I'll leave the stream on for a few more minutes. Yeah, so again, cutoffs, I don't see it as being like, so if we exclude the voided question, I don't see it as going any higher than a 13 or 14. It is very unlikely because there are just too many questions that also have possible careless mistakes inside, right? So if you have anything higher than that, it's quite unlikely that many people will have been able to score that much. Okay, I think most people have left, so I'll just end the session here. If you have any other questions or comments, just leave them in the comment section below. So thanks everyone again, and yeah, that will be all for now.